Okay, let's look at a graph of heating something up over time. Now, before we start, it's important to remember that temperature is the same thing as the average kinetic energy. So essentially the average speed of all those particles that are moving around. Now, let's say we start and our temperature, we're at time 0, and our temperature can start at this point here. And we start adding some heat or some thermal energy to it, and eventually you're going to see the temperature start to rise. So let's stop there, and we'll talk about what's happening. So we can say that we're in the solid phase, so we haven't started melting yet, we're just in the solid phase. And during this time period, our average kinetic energy, which I'm going to abbreviate using KE, this is increasing, and so the particles are moving faster. Now, as these particles are moving faster, the space between them, so the space between the particles starts to increase. So the space between the particles increases, and because of that, our potential energy, which I'm going to abbreviate using PE, this will also increase. So during this time period, kinetic energy and potential energy are increasing, and we can calculate this energy using Q equals mc delta T. Sorry, that doesn't really look like a triangle. So mc delta T, and we can use this equation to calculate thermal energy while temperature is changing because of that delta T. And so as our temperature continues to, or as our heat energy continues to increase, so we started off with this, but you'll notice that as you continuously increase the heat input, you're going to get to a point where the temperature kind of plateaus. And so here we're experiencing a phase change. So now, since we started with a solid, we're going from solid to liquid, which is also known as melting or fusion. And during this point, our intermolecular forces of attraction, which I will abbreviate with IMFs, these begin to weaken. So our intermolecular forces of attraction are weakening as we undergo a phase change. And the spacing between the particles increases, so our potential energy also increases. But remember, temperature is the same thing as average kinetic energy. And so our kinetic energy will remain constant. And because temperature is not changing, we can't use Q equals mc delta T anymore. We have to use Q equals mHF, or heat of fusion. And for water, HF is equal to 334 joules per gram. So it takes 334 joules to melt 1 gram of ice. All right, now let's continue with our graph here. So we started about here, we added energy, increased the temperature, we got to the phase change. Now once this phase change is complete, you'll see the temperature starts to rise again. So now we're in the liquid phase. And during the liquid phase, as we continue to add energy to it, so we're still heating it up, our kinetic energy starts to rise again, so kinetic energy is increasing. The spacing between the particles as you heat it up still increases, and so our potential energy will also increase. And because our temperature is changing, we go back to using this formula, so Q equals mc delta T. And so now, because we have a delta T, we can use this equation to calculate that heat energy input. And so kind of like for the last portion of this graph, so we went from here to here, we went through a phase change, right? Now we're in the liquid phase. And so the last part of the graph, well, almost the last part, now we're going to undergo another phase change. So this is phase change number 2. And so here we're going from a liquid to a gas, and this is vaporization or boiling. And so our kinetic energy is constant again, because we're not changing temperature, but potential energy is increasing yet again. So as long as you're adding energy or you're inputting energy, potential energy is going to increase. Now our IMFs, or intermolecular forces, they will weaken even more. And again, because temperature is not changing, we can't use our previous equation. So to calculate energy here, we have to use Q equals M HV, HV just meaning vaporization of water. And so for water, HV is 2260, that's joules per gram. So it takes 2,260 joules to vaporize 1 gram of water. All right, now for the last part of this graph. So we went from here, right? Started as a solid, increasing temperature, went through a phase change. All right, now we're in the liquid, going through another phase change. And now the last part, we can kind of increase this temperature almost indefinitely until you obviously reach some other temperature points, but we won't get into that. So now we're in the gas phase. And then during this phase, our kinetic energy is increasing because we're increasing temperature yet again. Our potential energy continues to increase as those particles get farther and farther apart. And because temperature is increasing and we have a change in temperature, we go back to using this formula for energy, and that's Q equals MC delta T. Now there is, you can also go in the reverse order. So the graph that we just looked at, that's a heating curve because we're heating something up. But there's also what's called a cooling curve. So I'll write that. This is a cooling. They're not really curves because the graph technically doesn't curve, but it's just what we call them. So it's a cooling curve. And so over time, as you kind of cool something back down, you'll see basically the reverse of the graph that we just made. And so in a cooling curve, potential energy is now decreasing throughout. Potential energy decreases throughout that curve. Kinetic energy will decrease, and this is only when temperature decreases. So again, during phase changes, kinetic energy still will remain constant. And then during this point, we have, instead of boiling, we have condensation. So that is the condensation point, but you're still going to use Q equals M HV. But now our energy is being released. So instead of energy being absorbed, now energy is being released as condensation occurs. And then for this point here, this is the freezing point. So we have the freezing point. And in this one, we can use Q equals M HF for fusion. And again, energy is being released. Sorry, it's a little messy. You can also use these graphs to kind of determine what the melting and boiling points will be. So if these temperatures, if this was actually labeled, you would be able to tell that, okay, if I just draw from this line over, I can tell what my boiling point is or my condensation point. And then if I draw from this line, or from that plateau over, I can tell what the freezing point will be. And so that's how you read heating and cooling curves.